Hi, I'm Joel, and I'm not paid. And you know, in life, you get what you pay for. So we'll see how this goes.
So this is Joel, and he's one of those people that when you'll see how it happens, but after he's done with this talk, you just I want to do what he does.
Uh-oh. Setting the bar high. I think everybody will want to do what Moshe does, but including myself. Well, welcome everybody. I, like Moshe, in fact, even worse than Moshe, I've got terrible handwriting. Now, I noticed there's an entire row of free seats at the front. So if people at the back have trouble... Oh, I see. They can. No, but they're below, right? I mean, where Moshe is. Below the radar. There's the entire French contingent there, and then there's some Polish... They probably cannot see, right? So... Not the second row. So, see how it goes. So I'm going to, Mikawai asked me to talk about, when he wrote that email to me, he asked me to talk about skolemoids. I love this name. So I'm going to, talk about that. And I'm going to be making it up as it goes. So basically, I've been in this sort of area, which I'll describe as I go, for some time, and mainly been doing research in that area. So, was that? Yes. It feels like that sometimes as well. I was going to make a joke about preparation something, but I've never actually given a course on this stuff. So this is going to be a little bit, this is, you guys are guinea pigs for, my trying to put my thoughts in order regarding this topic. I'm just wondering, is anybody taking notes? Probably several of you are. The cameras are taking notes. What people do in the US often is there's a note taker, somebody who takes notes and then produces nice latex version of these things. If anybody's inclined to do this, I'd be very interested in getting a copy of that because this would be a first step towards making a consistent body of introductory material on this topic. So if people are taking notes and they're willing to share them with me, or indeed with the rest of the class, then please don't be shy. And I'm sure Mikawai would. I mean, you'd be happy to disseminate, right, to people afterwards. Yeah. Right. Okay. So without further ado, okay. So I'm going to introduce this subject by just telling you some of the interesting problems that have led me into this area, and by way of motivation. So, unlike Moshe's world, my world is infinite. So I believe in the Turing machines, and numbers are not 32 or 64-bit integers and so on. They're the numbers as God created them. They're properly infinite and so on. And this is the context in which the questions that I'm asking about, I've tried to answer them. So suppose you start with a very simple question. So for instance, we can say, so I have X is a vector of variables, and I have a small program where initially I assign to X the vector A. And here A is going to be some vector of k-dimensional vector of integers. Okay? And then I have a while loop. And I'll say something like while some linear combination of the elements in X is not equal to 0. So I'm going to write this as U transpose dot X is not equal to 0. Do sorry about, I don't know why I'm taking this. Let me see if I can stabilize this board, lifting it a bit. Okay. X is a sign, let's say, mx. Okay, so this is a simple program. So here M is some matrix, some k by k matrix of integers. And I'm interested in interested, so A is some initial vector of integers, and I've got this program. This condition here, this is the dot product between some vector u and x. So this is just some linear combination of the elements in x with integer coefficients. And I'm saying while it's not equal to 0, simply iterate x is equal to mx. Okay, so m is just matrix multiplication. Does this make sense? So I'm interested in the halting problem for this kind of program. Okay, so I give you such a program. So in order for me to specify this program, I have to give you the initial vector a, the vector u that represents the exit condition, the guard of the while loop, and the matrix M, which is the linear transformation. Okay, there's no non-determinism or anything. And I ask you, does this program halt? Okay, and the question is, so this is a version of the halting problem, of Turing's halting problem. It is infinite memory because potentially these numbers can grow arbitrarily large. So if you implement this on a real computer, you know, you would have to have potentially unboundedly many bits, right? If everything is just one-dimensional and m is just the number 2, then you're just multiplying by 2 every time. And so, you know, obviously x will grow infinitely large, and you know this will never be true. But you know, if you're going to run this program, there's no a priori bound on the size of these numbers. Okay, now, so I'm asking the halting problem for this kind of program. And the question is it decidable? So we all know the halting problem is undecidable in general. What about for this restricted type of program? Okay, so anybody has a guess who thinks this is decidable? Okay, nobody thinks this is decidable. Okay, yes, the input is exactly that. That's the input. And the structure of the program is fixed. That's the structure of the program. So I give you this and I ask you whether that corresponding program halts or not. That's the problem. Okay, is this clear? Yeah. Okay, so who thinks this is a decidable problem, the halting problem for this class? Yeah, so we've got 3 people, 4 people, okay, 5, okay, 6, okay. Who thinks this is undecidable? We've got about 4 people. And who thinks, so we've got a lot of undecided people, I guess. Yeah, okay. Moshe, what do you think? No, I don't particularly want to spend it's one of the motivating problems, right? Okay, that's a good question. So, suppose I change this condition to greater or equal to 0, let's say. So this is a variation. Then, so the not equal to 0 is a little bit bizarre. This kind of question, this kind of pattern, that actually is quite frequent, right? If you look at code bases, this kind of loop happens a lot. You have to abstract a little bit because usually you'll have some non-determinism. You'll have some if then else. If you start adding some if then else, then it's easy to see, you can describe a 2-counter machine, so things are undecidable. But if you, let's say you've already done some over-approximation or some abstraction to remove non-determinism, the halting of these kinds of programs, this is what Terminator does, right? I mean, this is the kind of thing that people are interested in device drivers. They want to know, when you initialize a device driver, can you get caught in an infinite loop? Okay, so you know, these kind of questions, well, they arise naturally. I mean, Microsoft has built these tools, and they've actually found bugs in real device drivers and so on. So this is, this would be a little bit more natural, I guess. So likewise, for this problem, this is a similar question, right? So I had not equal to 0, now I have greater or equal to 0. So does this quantity ever become negative? That's the question. You halt if the quantity ever goes negative, and you don't halt if it always stays positive. You can see it's semi-decidable because if this quantity at some point goes below 0, then you can just run the program and witness this at some point. The hard thing is, of course, if it never does, you need to, in order to be sure that it doesn't halt, you need to exhibit some kind of proof, right? You need to, I mean, that would be the hard part. Of course, the halting problem for Turing machines is the same thing. If the machine halts, then of course you can see this by just simulating Turing machine for however many steps it takes, and it will halt. But if it doesn't halt, we don't know how to come up with a proof in general because it's undecidable. So that's one motivation. Another motivation is, I'm just running through motivations here, is Markov chains. Who has not heard of a Markov chain? Who doesn't know what a Markov chain is? I'm sure there's somebody who doesn't know what a Markov chain is. Yeah, one person, more, two. Okay, this is the only, okay, so most people know. I'm not going to define a Markov chain, so I'm just going to say that it requires a stochastic matrix. So stochastic matrix, and so this is a Markov chain over the states S1 up to Sk. Sorry? No, I don't want to say this because it's just a motivating example, and I will not come back to it again. Most people have actually, you know, I guess. So let's just, so you have some, I'm going to draw a diagram. You have some finite state system, and you have probabilities. So maybe you go from this state to that state S1, that state S2, that state S3. You go from this state with probability, from this state to this state with probability 1/3, from this state to this state with probability 2/3, and so on. So you got probabilities. And these probabilities are actually represented in the stochastic matrix. And you move around from state to state. And let's say you start in state S1. And at each step, you move according to these probabilities. So after n steps, there's a distribution, a probability vector that tells you what probability you are in each of the states, right? So initially, with probability 1, you're in state S1. But after one step already, with probability 1/3, you're here. With probability 2/3, you're there. And with probability 0, you're in S1, and so on and so forth. So there's a question, you could ask the question, is there a natural number n such that the probability that you're in state Sk after exactly n steps is equal to a half? Or you could ask the probability that you're in Sk after n steps is greater or equal to a half. Okay? So in order to give you a Markov chain, I have to give you this thing with these probabilities. I will actually give it to you with a stochastic matrix. It doesn't really matter. I will tell you what the start state is. And I can ask these kinds of questions. So suppose that all the properties are rational, which is what this would be here. Then you can ask again the question, are these problems decidable? Right? Can I decide? Can I decide whether there is an n such that after I'm in Sk after exactly n step, the probability that I'm in Sk after exactly n step is equal to half, or is greater or equal to half, etc., and so on and so forth. And it turns out this problem and these problems are interreducible. So if you put the equal 0 here, then that corresponds to equal to half, and the greater than corresponds to greater than, and you can interreduce. Okay, so this is just another motivation for these kind of problems. And I'm going to give one last motivation, which is automata theoretic. So suppose you have an alphabet sigma, and you have automata A and B. There are automata, finite automata over sigma, deterministic or non-deterministic. So these are NFAs. Okay, and suppose that you write as UN for every n. UN is the number of words of length n accepted by automaton A, and Vn is the number of words of length n accepted by automaton B. Okay? And suppose now I can ask questions such as, so there are questions you can ask about automata, such as, is every word accepted by A also accepted by B? And we understand how to answer these kinds of questions. But suppose I ask you, is there a natural number n such that the number of words of length n accepted by A is equal to the number of words of length n accepted by B? Right? Or is it the case, for instance, that automaton B always accepts more words than automaton A? Is it the case that for all n, Vn is greater or equal to Un? Okay? You can ask these questions. These are, I think, natural questions about automata. And again, these two problems are interreducible to this, these two problems here, with an equal or greater or equal. Okay, and you can ask other questions as well. You can, I mean, in fact, the kind of questions you can ask in this area, there's a whole plethora of questions. So for instance, you could say, well, I don't care about small n, but eventually is this the case, for instance? And then, I mean, there are actually lots and lots of questions you can ask. So I'm just giving you some motivating examples. Okay, does that make sense? Now, it may be a little bit surprising, but so these problems are not known to be decidable. Okay, they're not known to be undecidable, but they're not known to be decidable. They're known to be decidable for very small automata. So if the total number of states of the two automata is at most 4, then this problem is decidable. If it's at most 5, then this problem is decidable. So that's like really, really small, right? So I may be lying about this. Maybe I'm off by 1 or 2 or something. But it's you know, they very quickly, it's not that they very quickly become undecidable. They very quickly become hard to decide. And in fact, I'll try to explain some of these things as well. But I will you know, start with the basics. So we'll take some time to get to these problems per se. Okay. Any questions on this? Does this make sense? Okay. So let me leave these problems on for a while, and let me talk about just something else right now. So I want to talk about linear recurrence sequences. Okay, so what is a linear recurrent sequence? So these are infinite sequences of numbers. They can be real numbers, complex numbers. We'll mainly be dealing with rational numbers or integers. So, so a linear recurrent sequence, an LRS, and I'll write it as UN, n equals 1 to infinity, is an infinite sequence of numbers. So typically integers or rational and so on, such that there exists an integer k, and for all n, the nth term of the sequence is a linear combination of the previous k term, the terms that come, the n plus kth term of the sequence is a linear combination of the previous k terms that come right before this. So it's a1 times u n plus k minus 1 plus a2 u n plus k minus 2 plus ak u n for some a1 ak. Okay, so I should say there exists a k and there exists, let me just be precise, there exists a k and there exists a1 up to ak. Let me say here over the rationals, or the a1 up to ak depend on what you're taking the sequence over. So the best known example of a linear recurrent sequence is the Fibonacci sequence, which is defined by un plus 2 is equal to un plus 1 plus un. And in order to define a sequence, that's giving the recurrence relation. In order to fix the sequence, determine it uniquely, you have to give the initial terms. So if the order of the sequence, which is the number of terms, the k, number of terms depend to, is 2, then you need to give 2 terms. If the order is k, you need to give k terms. So I'm going to specify that u1 is equal to 1 and u2 is equal to 2. And now that uniquely defines the Fibonacci sequence. Sorry. It was meant to be 1. And that uniquely defines the Fibonacci sequence. Okay, does that make sense? So that's a sequence that has order 2. And linear recurrent sequences can have arbitrary order. And what I claim is that there is a very close relationship between those objects and the kind of things that I've described above. Now, if you look at the while program, for instance, okay, if you look at this while program that we've got there, what's really happening? Well, we want to know, is it the case that U transpose X is ever less than 0, right? That's what we're trying to determine, right? You look at the while program. Is it the case that U transfer X is less than 0? What's the first value that X has? The very first time, the very first test, when you run this program. A, exactly. So I'm going to write this as x1 is equal to A. Okay, so that's the first time. And so the very first test is whether U transpose A is less than 0. Okay? What's the next value that X takes? What's that? MA, right? So X2 is going to be MA. Then X3 is going to be, so that's not so good. I'm going to call it X0. X1, X2 is going to be M squared A. And in general, Xn is going to be M to the n A, right? And now every time I want to check whether U transpose times X is less than or equal to 0. So it makes sense to define the number un. Now this is let's say I'm working over the integer, so this is an integer. Un is defined to be U transpose M to the n A. Okay, so this is always an integer. Okay, and if I want to know whether this program halts, so the program halts if and only if there exists an n such that un is less than 0, right? Because you keep going while. So there exists an n so that un is less than 0. Okay, so this is the halting condition. Okay, that makes sense? Now, the claim is that if you look at the sequence un for n equals 1 to infinity, that's a sequence of numbers that's defined by this program. The claim is that this is a linear recurrent sequence. Okay, which is why I want to talk about linear recurrent sequences. And inversely, and I will show this in a second, inversely, if I give you a linear recurrent sequence over the integers, it can always be written in the form some vector times some matrix to the n times some vector. Okay, so asking about the halting of this problem is no different from asking whether a linear recurrent sequence is always positive or not. Okay, those two things are interreducible, which is why I'm interested in linear recurrent sequences. So these things have been studied extensively, obviously. I mean, the Fibonacci sequence, it actually has a journal dedicated to it. I mean, the Fibonacci Quarterly, which is a serious mathematical journal. It's just about the Fibonacci sequence. I mean, it sounds crazy, but there are lots of very deep results about the Fibonacci sequence. Like, for instance, here's something highly non-trivial about Fibonacci sequence. So Fibonacci sequence has got 1, then so it goes like this: 1, 1, then 2, then 3, then 5. Okay, so which are the perfects? 8. The problem is at 13. Okay, which are the perfect squares? The perfect squares are 1. And if you include 0 as part of this, you could actually say 0. So 0, 1, and it turns out you have 144, which is 12 squared in that sequence. And those are the only squares that you find in the Fibonacci sequence. And this is actually a very non-trivial result, right? I mean, this was proven not too long ago. There are no other perfect squares in the Fibonacci sequence. This is the kind of thing that mathematicians study. I mean, if Moshe asked me, what's the motivation for this? So ask the mathematicians.
Fibonacci square has many special properties. Are they special to Fibonacci, or they will...
The squares.
No, for example, the convergence, if I remember, to the ratio is the golden ratio and things like that. Are these properties special to Fibonacci? Do they show up in other LRSs?
No, they show, I mean, so I'll talk about the LRSs a lot, and there are lots of things, I mean, there's something specific to Fibonacci, but of course LRSs, there's a whole body of work on LRSs. Okay, so let me just, so I wrote here a claim that this sequence is a linear recurrent sequence. So let's try to prove this, right? Now, this is the first mathematical assertion I've made so far. So let's see if we can prove this. So let me just give myself some space. So the claim is that, so I'm going to write it this way. Let V and W be vectors in Q to the K. Let M be a matrix, a square matrix, a K by K square matrix. And let UN be defined by V transpose M to the N W. My convention is my vectors are always column vectors. And so in order to get a number, I need to do V transpose. This is a horizontal vector. M to the N, this is a vertical vector. So this is always an integer. Let UN be defined by this. And then I claim that then the sequence UN is a linear recurrent sequence. Okay? And so how would we prove this? So proof. So a lot of a lot of stuff I'm going to talk about uses basic linear algebras, but I assume that who has not had linear algebra or is not so happy with things like, you know, eigenvalues or the spectral, you know, the spectrum of a matrix. Who has never heard of the spectrum of a matrix? Come on, there's got to be one person. Okay, there's nobody or you're too shy. Okay, so...
no, you never do that.
What's that?
Ask people to, on the positive, who have heard of something.
No, people don't live there. Yeah.
No, ask who heard of something.
Okay, that's a good point. Who has heard of the spectrum of a matrix? Aha, Moshe, that's fantastic. Okay, I'm learning something. Great, okay. So look it up on Wikipedia later on if some of what I do looks mysterious. Okay, so so if you look at the matrix M, then we know that M is always a zero of its characteristic polynomial. That's the Cayley-Hamilton theorem. And so there's a polynomial, the degree of which is k, so such that m to the k is equal to a1 m to the k minus 1 plus ... plus a0 times the identity. That's the, let me just, hang on a sec. So m to the k is equal to a1 m to the k minus 1 plus ak times the identity. That's the Cayley-Hamilton theorem, right? If you compute the characteristic polynomial of a matrix, then every matrix is a zero of that characteristic polynomial. So I can rewrite these numbers A actually going to be integers, as it turns out, but in general they would be rationals. And now I multiply this equation on the left by what? By V transpose. So I get a V transpose here. So I put in A1 V transpose ... V V transpose the identity. I multiply on the right by W. So I've got this W here. And before I multiply by W, I multiply first by m to the n. So I add an n here, plus n, and here I have m to the n, and then I multiply by W. And now here I have u sub n plus k equals a1 u sub n plus k minus 1 plus plus ak u sub n, and therefore the sequence un satisfies a recurrence, a linear recurrence relation. So it's a linear recurrent sequence. Okay, does that make sense? Okay, and you can see that the order of the sequence is going to be at most the dimension of the matrix. It could actually be less, because every matrix is a zero not just of its characteristic polynomial, but its minimal polynomial. And the minimal polynomial may actually have degree less than the characteristic polynomial, in which case the linear recurrent sequence would have degree less than that of the dimension of the matrix. And we can go the other way around. So to go the other way around, I claim that let un be an LRS with initial terms, by definition, so u0 uk minus 1, and un plus k equals a1 un plus k minus 1 plus uk un. So I've got the initial terms. Let's say this is over Q, and then I want to claim there exists a matrix such that un is given to you by, there exists a matrix in two vectors such that un is given to you by this matrix. I just don't want to get it wrong, so I'm just going to copy. So I write, so then let M be the following matrix. So it's a so-called companion matrix of the linear recurrent sequence. So you write the matrix like this. You write here A1, A2, up to AK. Along the diagonal, you now put zeros. You put zeros everywhere else. On the super diagonal, you put ones. And you put zeros everywhere else. You write V as the vector UK minus 1, UK minus 2, up to U0. And you write W as the vector 0, 0, 0, 1. And you can show by induction, you can show that for all n, un is equal to V transpose m to the n W. And let's just check that it works for the base case. So when n is equal to 0, you have just the identity. So it's simply taking the dot product of V and W. The dot product in V and W is going to pick up U0. Okay, so you can see it works for the base case. And the super diagonal, you see what the effect it has is going to be shifting. Okay, you just need to work it out. It's just a simple calculation, and you see that it actually works. Okay, so the advantage of this is now we can switch from matrices to linear recurrent sequences seamlessly, because we know we can always, they're equivalent, the formulations are equivalent. You notice also the dimension of the matrix is exactly the order of the linear recurrent sequence. Okay, so you don't lose anything in terms of the order. Okay, does that make sense? Okay, so.
So my linear algebra has been some time ago. So this Katie Hamilton, this works
yes.
for fields. Does it also work like for Z or for the integers or?
Oh, what do you mean? Does it also work?
I mean, here to have this representation, this characteristic polynomial.
Yeah.
You're required to have the underlying structure to be a field. Like now you use Q.
This will always work. This will work in fields of any characteristic. Do you require it to be a field, though? You can always assume you have a field. I mean, if you have a matrix over the integers, you can always view it as a matrix over the rationals or over the reals. So what happens, I mean, the characteristic polynomial, if you've got a matrix...
The coefficients have to be rational, even if you start with integers. That's the point.
No, they're going to be integer as well.
So that was really the question. Why would you get integral coefficients?
Okay. So here's the reason. So what is the characteristic polynomial? So you write m minus t identity, and then you compute the determinant. So that p of t, so that's the determinant of m minus t times the identity. T is a real valued variable. And the determinant of that expression is the characteristic polynomial. Now, if you look at what happens, you have your matrix, and it's got some entries and so on. And here, you know, I'm going to write the entries, let's say A11, this is minus t, A22, this is minus t, and so on. And then elsewhere, you will have A12, you'll have the rest of your matrix. That's this. And when you take the determinant, okay, what is the term that's of order, let's say this is a k by k matrix. What is going to be, this polynomial will have degree k. The term that of order k is going to be given by the product of these guys, right? So it's going to be, when you compute this determinant, it's going to be A11 minus t times A22 minus t times dot dot dot. And so what is this? This is going to be plus or minus t to the k. The kth order term is going to be, when you compute the determinant, the only way you can get a kth degree term is when you take the product along this diagonal, and when you specifically take all the t terms. So it's going to be plus or minus depending on the sign, depending on whether k is odd or even, t to the k. The leading coefficient will be 1 or minus 1. So this is why they're always going to be integral coefficients. Not that this matters. I mean, this is neither here nor there, really. Okay, does that make sense? Moshe, you convinced? Yeah. Okay, so, but this is how you compute the characteristic polynomial. You don't need a field or anything. You don't need to make any assumptions. You just do this calculation. You know, it just compute away. It just has to be a ring, really. In fact, yeah, I'm being silly. The Kalium, it just has to be a ring. You never divide. You just multiply. So you just work in a ring. Okay, so let me talk about something else. I was going to talk about this at some point, and might as well talk about it now. So something interesting. Moshe mentioned the pigeonhole principle. So let me tell you about the very first use of the pigeonhole principle. The term was, the pigeonhole principle was sort of invented or discovered, although as Moshe says, I mean, and this is a result for you. I mean, it makes us look a little bit comedic. Although as Alfred North Whitehead said, it takes an uncommon kind of mind to see the significance of the obvious. And the pigeonhole principle is an incredibly powerful principle. So being able, having it stated is, yes, it's very obvious, but on the other hand, it's good that it exists. So it was first formulated, at least in the literature, by Dirichlet, who was a French mathematician, who wrote both in German and in French. But in the French literature, he called it le principe des tiroirs. And he had this, principe des tiroirs talks about the principle of the drawers. And he had this idea that if you have, 6 drawers, and you put 7 pairs of socks in these drawers, then you will have one drawer that has 2 pairs of socks. And Dirichlet's father was a... That's true, that the washing machine eating the socks. Yes, absolutely. Which is why it took so long to discover. And Dirichlet's father was a postman. And in fact, in the post office, you put all these letters, you sort them into these little cubicles. Now, in English, these are called pigeonholes. And this is where, because they do resemble the kind of holes that pigeons. But this is the idea that if you have, 7 letters, you put them into 6 of these pigeonholes, these boxes, you will have 2 letters in the same. So this is where actually it actually came from. Of course, this is inspired from the... and so what did Dirichlet use these? So this was about 1830s. I don't remember the date. What did Dirichlet use the pigeonhole principle for? He used it for a very interesting... he used it for a very interesting purpose. And I'm just trying to remember. Okay, so this is the complex plane. That's right. That's right. Until that point, it was true, and then. So this is the complex plane, and this is the unit circle in the complex plane. And suppose that you have a complex number. I'll just represent it as I'm calling it lambda. That is not a root of unity. So how can I write this? So lambda to the k is not equal to 1 for any k. Okay. So just trying to think. He shows something slightly stronger, but let's just go with this. Now, what Dirichlet showed is that if you look at so lambda is a complex number of modulus 1. So this is lambda. This is going to be lambda squared. This is going to be lambda cubed. And he showed that if you look at the iterates of lambda as n ranges from 1 to infinity, the points that you hit are going to be dense on the circle. Okay? And how did he show this? He said, well, I need to show that for any, if I take any point and I take an epsilon neighborhood around this point, I'm going to have some lambda to the something, eventually enter that neighborhood, right? So the way that Dirichlet showed it, he said, so let epsilon, some epsilon be pick some epsilon, some little neighborhood, and now divide the circle into epsilon pigeonholes, epsilon size pigeonholes. And if you look at the numbers lambda squared, lambda to the k, where k is bigger than 2 pi over epsilon. Okay. So you've got an epsilon size box, and you've got another epsilon size box, another epsilon size box, and so on. And in total, you've got the number of boxes you have is 2 pi over epsilon. Okay. So if you take a number k that's actually bigger than the number of boxes, then you know that there will be I and j, such that lambda to the I. Oh, that's terrible. Okay. J, there will be S and T. It's just bad to use I when you're talking about complex numbers. So lambda to the S and lambda to the T will be in the same epsilon box, will be less than epsilon distance apart, right? Okay, so these guys will be less than epsilon distance apart. So I'm talking about the absolute value. Really, I should talk about the angle, but it's basically the same thing. And so, and T is the bigger one of the two. And so now, now what you can do is if you look at lambda to the T minus S, then lambda to the T minus S will be in that, will be either in that epsilon box or that epsilon box. So basically, lambda to the T minus X will be within, minus 1 will be within epsilon of the origin, right? Does that make sense? Make sense, everybody? Okay. So, so now what happens is that if you're trying to enter an epsilon box that's here, and there are n epsilon boxes up to there, then what you do is you do lambda to the t minus s times lambda, to the n. No, sorry, what am I saying? I want to do, hang on. No, sorry. So if I look at lambda to the t minus s, and then I actually square this, then I've moved, so lambda to the t minus s is in this epsilon box. So if you square it, you're going to still be in that epsilon box or go, a little bit above. So what am I trying to do? I need to raise it. I need to raise this to a power n, such that such to a power n, such that I'm in the box that I'm trying to shoot for. Sorry, I'm making a bit of a mess of this, but you see what's going on. Okay, lambda to the t minus s is very close to the origin. So when I actually square that, then I'm in the next box basically, or and I keep increasing by less than epsilon every time. So I'm basically can reach any box that I want by iterating this long enough. So the number in question is going to be lambda to the t minus s times n is going to hit the box in question. Okay, does that make sense? Okay, so this will come in handy later on. Right. So let me talk about solutions of linear recurrent sequences. I'm going to use it at some point. Yeah, it will come up later. Actually, Derek showed something a little bit stronger, which is basically this proof. He showed that for any x, it's basically the same proof. For any x, so for any x in R, if you look at x minus p over q, and you want this to be less than 1 over q squared for some pq integers, you want to know, can you find infinitely many p's and q's such that x minus p over q is less than 1 over q squared? And he showed that you could always do that. And it's basically the same proof of this, as this. So it's a little bit stronger than this, actually. And this is in the complex plane. This talks about, this really talks about the fractional part of x. I mean, you can, it's the same proof, phrased a little bit differently. Anyway, we'll be coming back to this later on in the course. But I just thought I'd mention it because you talked about pigeonhole earlier, and this will come up. So let me. Okay, so Fibonacci sequence. So un plus 2 is equal to un plus 1 plus un. So that's very nice. What is un equals to? Do we have a formula for un? Does somebody know? Yeah?
Square root of 5 minus 1 divided by 2 to the power n.
Yeah. So I'm going to write it as 1 over root 5.
And it's, I think,
5 to the power n minus.
Yeah, divided by 2.
Yeah.
To the power n, and the same with minus.
Yeah. So in general, you have a closed form formula for the Fibonacci sequence. And indeed, it has that form. And we'll see this is not an accident. This is a general thing about linear recurrent sequences. Let's just see. So suppose I try to have the linear recurrent sequence un is equal to, let's say just un is equal to 1 for every n. What linear, how could I achieve this as a linear recurrent sequence? This is very easy. Yeah, so un plus 1 equals un, and u0 equals 1. Bingo. Okay, a little bit harder. What if I give you, I ask you to, un is equal to n. How can I achieve this? Is this correct? So who says yes? It's not homogeneous, that's right. It's not the definition of linear recurrent sequence I gave. Because you're allowing yourself to have a constant term here, and I didn't allow that. Okay, so could we do it without a constant term? Yeah. So un plus 1. Yeah, okay, so let me write it like this. And then again, u0 equals 0, u1 equals 1, and I have that. Right? Does that make sense? I mean, you can check, right? So the term u2 is going to be 2 times 1, which is 2, minus 0, so that's good. u3 is going to be 2 times 2, which is 4, minus 1, which is 3, so it actually works. Okay, but it's order, but you notice now the order here, the order is 2. Could I get it as an order 1 linear recurrent sequence? Who said no? Why is that?
I know the solution,
So the simple answer would be if you had un plus 1 is equal to a times un, and un is equal to, u0 is equal to some constant k. If it's 0, then the sequence is identically 0. If it's k, then you'll have that un plus 1 is equal to a to the n times, isn't that right? Times k, right? So basically, it can never be just n because you're multiplying by a every time, right? So it's going to be exponential. If it's order 1, it would have to be exponential. Okay, so that can never be equal to n. For all n, you can never have this equality, right? This is kind of obvious. Okay, okay, so that's correct. Okay, so suppose, let me give you something. So suppose I want un equals n squared. Can I do this? Yeah, we talk about linear recurrent sequences. N squared is not linear, is it? That's a bit confusing. Okay. Unless the exponential, the a is 1. Right? Using a third order. I see somebody has had courses in linear recurrent sequences before. Yes, it's possible to do. I don't know how to do it right now off the top of my head, but definitely it's possible to do. We'll see this as we go on. But actually, I can't actually write down what it is. I mean, it's not. Sorry. Sorry.
According to that, let's look at the next term. Un plus 1. Un plus 1.
Un plus 1, yeah.
Right.
So that would be n plus 1 squared. So you're saying that would be n squared plus 2n plus 1.
So L squared is okay, the previous element, but somehow you'll have to find something to capture.
It'll be 3.
Oh, you'll have to do it as difference of square. No, you have to do it as some difference, yeah. You have to capture the difference between squares, yeah. Probably do it.
Yeah, I mean, certainly doable. I mean, I can prove it's doable. It's gonna be order 3. It'll have to be order 3. I can prove that as well. I don't know what I mean. It's interesting. I should have prepared this better, but you know, there's probably a simple thing. Okay, so you're saying un plus 3 is equal to what? 3 un plus 2 plus minus 3 un plus 1, and then the un plus un. Okay, let's see. So, and we have u0 is, we want to say 0, u1 is 1, u2 is 4. So let's compute u3. So u3 would be 3 times, so u3 is supposed to be 9, right? So that would be 3 times, you're saying 3 times 4 is 12, minus 3 is 9, plus 0. Yeah, so that seems to work. Well done. So that's a proof, right? So I'm almost certain this will work. Yeah, well done. Okay, so this is interesting. Linear recurrent sequences are quite rich. If you take a step back and you think about the problems that we're asking, so a problem that people have been asking since antiquity is if you have a polynomial p, let's say p of x, which is, let's say, a polynomial in one variable, then you can ask the question, is there a real number x such that p of x is equal to 0? Does the polynomial have a 0? You can also ask, is there an integer 0? Okay. And it's quite easy to see, I mean, it's certainly true, that linear recurrent sequences form a richer class of functions than polynomials, right? We saw that we could get n. We saw that we could get 1. We saw we could get n, which could get n squared. It's actually not hard to see that you can get n cubed and so on. And the good thing about linear recurrent sequences, they form a vector space. If you've got 2 of them, you add them, you again have another one, and so on and so forth. And so you can get any polynomial, but you can also get exponentials within, right? And the kind of questions we're asking are, so these are questions we're asking about zeros polynomial or positivity of polynomial, right? Is it the case that for all x in R, for instance, you know, p of x is greater or equal to 0? And for linear recurrent sequences, we ask the same question. We're asking, is there an n such that un is equal to 0, or is it the case that for all n, un is greater or equal to 0? These are the kind of questions, if you remember from the beginning, these are the questions I'm asking. So they're kind of generalizations of questions you can ask about, you know, zeros of polynomials, which are questions that have been asked for a very long time. Okay, so if you look at it in this way, linear recurrent sequences are interesting objects to study. From that point of view. How am I doing for time?
Well, 12:30.
12:30. Okay. Okay. So let me continue.
So how much can you take from undecidability of this side? We have different equations, undecidable.
Yeah. So there are no undecidability results that are known, but towards the end of the course.
That's what I'm saying. Since you said it's very close to polynomial,
yeah.
This kind of questions. So this kind of questions, right, is decidable for reals and undecidable for.
No. This is decidable.
One variable. One variable.
This is decidable for.
Oh, this is one variable.
One variable. That's right.
Yeah.
That's right. Yeah. Yeah. It's you can. Yeah. That's right. So Moshe was thinking about Hilbert's 10th problem, which is asking whether a multivariate polynomial has a 0, whether that's decidable or not. That's known to be undecidable by Matyasiewicz's proof of the undecidability. But we're just in the one variable realm. Yeah. Okay. Let me actually. Yeah. No. Go. Yes. So the Hilbert one variable thing would be asking this question, right? Yeah. So this is decidable. You can look at it. You can show it's decidable in various ways. The easiest way, maybe I can convince you, is decidable, is that the existence of zeros is decidable by Tarski. Okay, and you can use the existential theory of the reals to get arbitrary approximations of the zeros. So you can say, is the zero bigger than this number, less than that number? You have an existential theory of the real oracle. You get closer and closer. And depending on the height and the degree of the polynomial, meaning the degree of this thing and the magnitude of the number, you know that you cannot get too close to an integer unless you are that integer. Yeah, the problem is that the problem would be this. Suppose you had a root that was incredibly close to an integer. How do you know when it's not or when it is? Oh, you could do this as well, of course, yeah. You apply it to this integer. Yeah, of course, that's even, yeah, okay, sorry. But this will come later, yeah, that's a very good point. There are times when you, yeah, okay, that's even better. That's convincing, right? Yeah. Okay, but it's not clear at all, you know, what goes on here. And in fact, there are some hardness results that I'll show later, but they're not undecidability results. They're, you know, hardness with respect to other things. Okay, let me just tell you a little bit more about the structure of linear recurrence sequences. Suppose I have a linear recurrence sequence UN, and I have a linear recurrence sequence Vn. And suppose that I write WN to be UN times Vn. So pointwise, every WN is UN times Vn. Then I can ask the question, is the product, the pointwise product of two linear recurrent sequences, again, a linear recurrent sequence? And if we know this, then we know that n squared would be a linear recurrent sequence, because we know n is a linear recurrent sequence, therefore n squared would be a linear recurrent sequence. And actually then completely tells you that linear recurrent sequence contain all the polynomials. Because obviously constant times, they're also closed under multiplication by constant. That's obvious. Okay, so the answer is yes. And let me show you the proof. It's a very instructive proof, and it's exactly the same argument that you would use to show that, I mean, everybody knows that the algebraic numbers form a field, right? If you take algebraic numbers, these are solution of polynomials with integer coefficient. And we know that if you take two algebraic numbers, you take square root of 2 and cube root of 7, we know that this is actually an algebraic number. But nobody, I mean, does anybody really know how to compute the polynomial such that this is a root of, you know, it's an algebraic number, so it's a root of a polynomial. Do people, you know how this is done, or do people? Well, most people, in my experience, they just know this fact. They know that algebraic numbers form a field. They don't know why. And it's the very same proof that linear recurrent sequences are closed under multiplication, and they're also closed under addition, by the way. I could, if I added them, then this would also, again, be a linear recurrent sequence. So let me show you this. Addition is not completely trivial. Not completely. But it's the same proof. It's going to be the same proof. And it's the same for algebraic numbers, by the way. So an interesting exercise, if you want to do it tonight, I'll do this now here for linear recurrent sequences. Go and think how to do this for algebraic numbers. It's really the same thing. And if you remember nothing else from this course, you'll remember this. This is knowing why the algebraic numbers form a field, which is a really important fact, is a nice thing to know. Okay, so how do we do this? I'm going to do multiplication because it's actually harder, but I mean it's the same thing. So I'm going to prove that then this is a linear recurrent sequence. So, okay. So we have UN to be a linear recurrent sequence of order k. So we'll say it's A1 times UN plus K is A1 UN plus K minus 1 plus dot 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 plus AK UN, and we have that Vn plus L is equal to B1 Vn plus L minus 1 plus BL Vn in general. And now what I want to do is I want to consider the set Q to the omega. So this is the set of all Q infinite Q sequences. Okay, so this is the set of all sequences containing rational numbers, not necessarily linear. Okay, not necessarily linear. And I want to consider a set S, which is a subset of Q to the omega. And S is spanned by the following sequences. So I want to span S by the sequence UN Vn for n equals 1 to infinity. So UN Vn, pointwise, this is a sequence, right? It's an infinite sequence. Okay? So it lives in that Q to the omega. And I want to consider the Q vector space S, so spanned over Q. Okay, so I'm going to define a vector space spanned by a certain number of vectors. So I'm viewing this as a vector space. Okay, I mean, it's clear it's a vector space. If I take two infinite sequences, I add them pointwise, again, I get an infinite sequence. I multiply by a rational number pointwise, I get an infinite sequence, and so on, right? So it's a vector space. And I'm considering a subspace S, okay, spanned by the following sequences. This one, UN plus 1 Vn, n equals 1 to infinity. UN plus K Vn, n equals 1 to infinity. UN plus, whoops, UN plus 1 Vn plus 1, sorry, UN Vn plus 1. That's a dot, n equals 1 to infinity. U n plus k times v n plus 1 is 1 to infinity, and so on and so forth. And finally, u n v n plus l, n equals 1 to infinity, all the way up to u n plus k v, whoops, times vn plus l, n equals 1 to infinity. Okay, so I repeat. These are honest-to-God sequences that are given to me because I have initial condition. I have u0 equals something, u1 equals something up to uk. I'm given this. I'm given v0 up to vl, and I've given a recurrence relation. So un and vn are infinite sequences. They live in Q to the omega, which is an infinite dimensional vector space. Okay? Right. Now, I can pointwise form the sequence un vn. This is the sequence that actually interests me, by the way, because that's my wn, but never mind that. I can pointwise form the sequence un plus 1 times vn. That's an infinite sequence, and so on and so forth. And I can consider all these different products of combination of the form uj, un plus j, vn plus r, for n equals 1 to infinity, where j and r, where j ranges from 1 to k, and r ranges from 1 to l. Okay, so I look at all such sequences. These are all sequences. They're all in Q to the infinity. And S is the vector space, the subspace of Q to the infinity, spanned by all these guys. Okay? Everybody with me? What is the dimension of S? At most? That's right. So everybody see this? Dimension of S is at most KL, because it's spanned by K times L different vectors in S to the omega. So it has, I mean, this is a spanning set. So clearly the dimension has got to be at most the cardinality of any given spanning set. No, because I think, oh yeah, sorry. Yes, so here, let me stop at -1 and -1. I think this is enough. And here I'll do -1 and -1. Thank you. So here I'll stop at -1, -1. Yeah, thank you. So at most KL. Okay? Right. Now let me actually write the following. I know that Wn is equal to Un Vn, because that was my definition. Okay? As sequences, they're true. I know that Wn plus 1, well, what is it? It's Un plus 1 times Vn plus 1. I know that Wn plus 2 is Un plus 2 times Vn plus 2, and so on. And I know that n plus k times n plus kl is u sub n plus kl times v sub n plus kl. Right? I can write these equations, and I have KL equations. And I think, I think I want this, no? I think I want a -1 there because, is that right? No, maybe not. Okay, so how many equations do I have here? I've got, I don't know, it's okay. How many equations do I have? KL plus 1, right? Okay, now, when I'm writing this here, at some point, I will have, somewhere, I will have u sub n plus k times v sub n plus, I don't know, let's say r, right? At some point, I will have some u sub n plus k. I can replace this u sub n plus k. Yeah, that's right. That's right, yeah. That's n plus k. But let's say that L is bigger than k, so this stays. But un plus k, I can replace this un plus k by the definition of un plus k, which is some linear combination of un plus k minus 1 and so on and so forth. So here, when I write w n plus k, I can replace this un plus k by some linear combination, which is going to be a1 u n plus k minus 1 plus ... times v sub n plus k. Okay, so I can do this. Everywhere. So I never have a u n plus k or anything above, and I never have a v n plus l or anything above. Okay, right. Now, each of these sequences, therefore, belong to S. Okay, because they're all S is a vector space, and these are all spanned by the spanning set of S. Okay, so if I look at these as vectors in S, I've got KL plus 1 vectors in a KL dimensional vector space. So what do I know? I know that they have to be dependent. So I know that there's going to be some linear relationship amongst those guys, right? Because now these are vectors in S. So I know that there's some combination such that C1 W1, C1 Wn plus C0 Wn plus C1 Wn plus 1 plus ... plus C KL W n plus KL equals 0. And if I assume that this CKL is not 0, that means I can write Wn plus KL as some linear combination of Wn plus KL minus 1 ... Wn. Okay? if this guy is 0, then I get a linear recurrent sequence of smaller order. Does that make sense? Yeah? Okay. It's a little bit abstract, but it's exactly, is this convincing? Maybe it takes some, if your linear algebra is a bit rusty, just need to stare at this for a little bit. The exact same proof works for showing that the sum of two linear recurrent sequences is again a linear recurrent sequence. So it's a independence argument. Yeah?
Getting caught up. So you wrote out W's, which are the product of U and V at the same index.
Yes.
You replaced W, like UN plus K, with U's at a different index.
Yes.
So how did you get then a recurrence in W?
Okay, so let me go through that argument again. It's a good question. So what I have here are linear combinations of UN plus something, Vn plus something, but I never have any term equal or bigger than UN plus K in terms of the index, or bigger or equal to Vn plus L in terms of the index, right? They're all in terms of Vn plus something less than L and Un plus something less than K, right? Because I can always do this replacement. Okay, now, and these are just linear combinations, so, because I have A1 times something, so they're a linear combination of these sequences. So think of them now as sequences. We're thinking of the sequences are equal to these things, right? These are sequences. These sequences, so they're members of Q infinity. They're not just members of Q infinity, they're members of S. Because S is spanned exactly by all these products where the indices are less than n plus k less than or equal to n plus k for the U and less than or equal to n plus L for the V's, right? So they all belong to S. And so I have KL plus 1.
Between Wn, the sequence Wn and the sequence Wn plus 1.
Sorry?
What's the difference between the sequence Wn?
Okay, so
if you think of Wn plus.
Yeah, that's a good. Yeah, so the sequence, if you look at the Fibonacci sequence, is the sequence 1, 1, 2, 3, 5, etc. That's a sequence in Q omega, and the sequence Fibonacci plus 1 would be 1, 2, 3, 5, and that's the that's also a sequence there. And these are two different sequences. Because n goes always from 1 to infinity. So the n plus 1, the n goes from 1 to infinity. So it's a sequence that's shifted by 1. Okay? So I have these Wn plus 1, Wn plus 2. Because they're linear combinations of things in S, each of these guys belongs to S. Okay? So I have KL plus 1 vectors in S. These vectors have to be linearly dependent because S has dimension KL. Yeah?
So it looks like at the end you have to divide. Is this true for an RS over Z?
You don't have to divide because no, you don't have to divide. Sorry. Yeah, but that's not going to happen. It's always going to be 1, basically. Yeah, I mean, you could work it through. So if you take two Z linear recurrent sequences, you always get, the product of them is always, they're always going to be integers. They're always going to be a Z linear recurrent sequence.
Suppose instead you just think of it, you just, okay, I'm guessing the dimension is going to be, because the product dimension is going to be KL.
Yeah.
Now you're looking for the coefficient.
Yeah.
And you write it, you obtain an equation and you solve the equation and you get a direct and constructive proof and maybe more transparent than going to the dimensionality.
Well, the problem is, how do you know the dimensions at most KL? Well, it's a guess. Ah, okay. Wow. No, but here I don't guess. I prove that the dimensions at most KL because I have this thing which is...
you have to make the same guess by creating the basis here. You had to guess that you made the same guess by creating the basis here.
Well,
you made the guess escape. How did you know to start with this particular?
No. Fair enough. I made a guess, but this is a proof, though. This is a proof. If you just say, I'm going to guess that the product of a linear recurrent sequence of order 2 and one of order 3 is one of order 6, and then you solve the equations, you don't know for a fact that the order was high enough or that, you know, this is always going to work. Whereas here I prove it.
I suspect you can prove it generally in abstract way, and it will give you the coefficients directly.
I think this is one of the simplest proofs, Moshe, honestly. I think it's going to be hard to get a simpler proof than at some point you'll have to use dependence of vectors in a finite dimensional vector space. I don't think you can do it otherwise.
I mean, I think an alternative view is for linear recurrent sequence that you have some additional registers that you use, yeah? Like instead of computing one number, you have compute a vector of numbers,
Yeah.
and based on a linear combination
Yeah.
of the previous
Yes.
number.
Yes.
And that's equivalent
Yes.
view.
Yes.
And I think if you have these registers, then the multiplication is easier to understand.
I see.
And I think you can just directly do it.
Okay.
You just keep in the end you're interested in the multiplication, but in your auxiliary registers you keep multiplications of other terms corresponding to this matrix.
I
And
see.
I think it's just...
But you'll still need to use the fact that you've got finite dimensional vector space, right? Then you've got a...
Well, implicitly, but you don't see it.
You don't see it. Okay.
Okay, it's possible. I think this proof is very simple once you just wrap your... I mean, I think it's actually a very simple proof somehow. I mean, I'm making a bit of a mess of it perhaps here. But it's conceptually, yeah, I think it's simple. But yeah, there are other ways to do it. By the way, if you go to the matrix form, then you can use the Kronecker product of matrices to get an expression immediately. I think that's more complicated, by the way. What you have in mind. Okay, so this, yeah, I see. So you can do it, if you know about the Kronecker product of in linear algebra, then this is immediate. This is going to be immediate, yeah. You have a matrix for the UN and a matrix of Vn, and you take the Kronecker product of the two, basically. This here? Not exactly. You basically, when you've got this matrix and then this other matrix, you replace, you stick in this matrix here in all these, you sort of insert this matrix within this one at every entry. It may be this one. I'd have, yeah, it's possible, yeah. I mean, I'd have to sort of think it through. But basically, it's a simple, I mean, yeah. And the corresponding matrix, which is of dimension, you've multiplied the dimensions, is going to be the matrix corresponding to the new WN. So I think I'll stop here. Are there any remaining questions or residual doubts about this? Yeah?
So if you want to take the sum of the two sequences,
Yeah.
with this, how does the order grow? Like some...
Just the sum of the orders. Yeah. And you can just do it. It's the same proof. And if you want to, and for algebraic numbers, it's interesting, but you know, having seen this, now you can show that the sum or the product of two algebraic numbers is an algebraic number. It's really the same idea.
Another question, so are those linear sequences closed under taking away a finite prefix? So like
Yes.
15?
Yes.
The reason they are is that the recurrence holds for any n. So taking away finite prefix just means changing the initial terms. Okay?